So welcome student, today we will study about the pervaporation process. So pervaporation is the combination of two processes, permeation and evaporation. So in this process, we combine the membrane based permeation process with the evaporation. So this is the specific type of membrane based process where the phase change occurs during the separation. So here this is the feed side. Here liquid enters in the feed channel from this point and flows from this direction. And the different feed species or different components present in the feed permeates through the membrane from here to across the membrane from here to here. So this is the permeate side. So um, uh, once the different components approaches to the permeate side, they vaporize and they comes out from the permeate side in the vapor form. So it is a combination of two processes, permeation and vaporization. So basically in the pervaporation processes, in the pervaporation process, the separation occurs in three different stages. First, the different species present in the feed absorb at the surface of the membrane, absorb as the surface of the membrane. Then they will these absorbed species diffuses across the membrane due to the concentration difference. Then they will dissolve at the other side of the membrane in the vapor form. So for vaporization, we generally use two different processes. In first process, we use the vacuum pump to create the high vacuum in the permeate side. Due to the high vacuum, the desorption occurs in the vapor phase. Or we can use the carrier gas like N2 or like nitrogen or helium in the permeate side. So due to these gases, the partial pressure of the dissolved component will reduce and they will dissolve in the vapor phase. So the first question arises that what is the benefit of the vaporization in the membrane based separation process. So to understand this thing, we have to compare the pervaporation process with the reverse osmosis. In reverse osmosis, we separate the salt from the water. So the reverse osmosis membranes are selective for the water, not for salt. And in the salt water mixtures, the water present at the higher concentration. So when you separate the salt and water and salt from the by using the reverse osmosis process, the concentration of water is generally 99.9% and the concentration of salt is very minute, that is less than 0.1%. At that time we use the reverse osmosis process and the membranes are selective for the water. So when you have the higher concentration of the selective component in the feed side, so they can easily absorb, easily diffused and easily, most importantly, easily dissolved from the permeate side. Now suppose you have prepared you have a type of mixture where the membrane is selective for the solute, not the solvent. Suppose you have the water alcohol mixture and you have a membrane which is the hydrophobic membrane, and that membrane is selective for alcohol, not water, and concentration of alcohol in water is suppose is less than 1%. Now that if that minute amount of alcohol is absorbed on the surface of membrane and that diffused at the other side of the membrane, then it is very difficult to dissolve that minute amount of alcohol from the at the permeate side. It will not dissolve easily. Why? Because concentration is so low of alcohol in the mixture that it will saturate the membrane but it will not dissolve from the permeate side. So for removal of the for desorption of that alcohol from the membrane, we have to use a driving force, and that can be provided by the vacuum or by the carrier gas. So that driving force is the phase change. So when the phase change occurs, then the from the liquid to the vapor, then the molecules of the dissolved component can easily moves from the permeate side, or it will rapidly removes from the surface of the membrane. So basically pervaporation process is used to separate the liquid mixture where the one component is present in the minute amount, and that component is selectively separated by the by the membrane. So in this diagram it is also shown the which type of mixture can be separated from the pervaporation process. Here you have the water dioxide mixture. So if you see if you check the vapor liquid equilibrium of water dioxide mixture, it make the azeotropic mixture. So what is the azeotropic mixture? Azeotropic mixture are the mixtures where the boiling point of both component are nearly equal, so they cannot be easily separated out by using the traditional distillation process. So this is the mole fraction of water in the vapor, and this is the mole fraction of water in the liquid, in the vapor liquid equilibrium. So you can see that at the lower concentration of water, if the water is present in at very low concentration in the liquid, then the in vapor phase you have the higher concentration of water can be vaporized at higher concentration. But when you increase the concentration of water in the liquid, then you will see the opposite result. Then the dioxin concentration will increase in the vapor phase in comparison to the liquid phase. So this is the type of water liquid, this is the type of where azeotropic mixture. So this type of mixture is very difficult to separate by the traditional distillation process. In the traditional distillation process you need a third additive which can separate out this two component. So in pervaporation we can use a membrane which is the either hydrophobic or hydrophilic. So the membrane may have the higher affinity towards the water, or membrane may have the higher affinity towards the organic compounds. So if membrane have the higher affinity towards the water, then the water will selectively diffuse across the membrane, then it can be easily vaporized. So you can easily shift the equilibrium by in the pervaporation process. So in the distillation process you have the this equilibrium graph, and in pervaporation process you have the this equilibrium graph. Now the advantages of the pervaporation process over the other processes. So first is the no additives is required. So in if you are generally, as I told you that the pervaporation process is used to separate the azeotropic mixture. So if you are using any traditional separation process, then you need the azeotropic additive to separate out that liquid. But here we are using the selective membrane, so you are not any additives is not required. Second is the low energy requirement. Low, why? Because here the A component is uh, selectively permeating through the membrane, so that only component has to be vaporized. If you are using the distillation, then the both component will be vaporized. So here the requirement of energy is relatively low in comparison to the traditional distillation process. Third is the no reactive process, non-reactive process. If we use any reactive process to separate out any compound from the mixture, then that compound will be destroyed due to the reaction. But it is a physical process, so you have the two different streams where one stream contains the, if you check the diagram, then you can see that if you check this diagram, so the one species will selectively diffuse out from the membrane. So you have the higher concentration of one species in the permeate side, and you have the higher concentration of the other species in the rejected side, or the rejection side. So here you have the two different is output stream. One contains a single component, and second is stream contains the second component. Now fourth advantage is this process can be used in continuous manner. So if you compare this process with the processes like absorption or adsorption, so the additives used in absorption or adsorption will be saturated out after some time and require the regeneration. But this is a continuous, membrane based processes are continuous process, so you need not to regenerate the membrane, and this process can be used without any delay or without any stoppage in the process. Now, fifth advantage is lower capital cost as compared to distillation. So we know that the distillation setups are huge setups and that require a lot of capital cost, but generally membrane based pressure setups are very small in size and that required a very relatively small low capital cost. Now the different type of membranes used in this process. So generally we use the membrane used in the pervaporation process can be classified in three different types. First is the hydrophilic membranes, second is the hydrophobic membranes, and fourth is the membranes which are used to organic separations. So generally hydrophilic membranes means the membranes which has the membranes which have the higher affinity towards the water, for like the polyvinyl alcohol membranes, PVA membranes. So these type of membranes can be used to separate the water from the water organic compound mixtures like water alcohol mixtures. So you can separate the water can be selectively permeates through the membrane and then vaporize at other side, and you can separate out the water minute amount of water present in the liquid from the water alcohol mixture. Second type of membranes are the hydrophobic membranes, which has these type of membranes have the higher affinity towards the organic compounds. So you can use this type of membrane to separate out the organic compounds from the water. So the suppose you have the water which contains the small amount of organic impurities like alcohols or like aldehydes or ketones or phenols. So you can remove that phenols or ketones from the water by using the silicone type membranes. So these organic compounds will be permeates out selectively through the membrane, then will be vaporized in the permeate side. Third type of membranes are the membranes which are used to organic separation. So like modified cellulose ester membranes. So these type of membranes are used to aromatic paraffinic separations like toluene and heptane separation, or olefinic paraffinic separation like an heptane and heptene separation, and paraffin separation like isooctane and octane separation, or high molecular weight paraffin to low molecular weight, ultra high molecular weight or low molecular weight paraffin separation like hexane and octane separation. So these are also the major application of the membranes. So basically the potential application of perforation process can also be defined by this classification. So these are the some commercial application of perforation process. First is the separate for separation of the mixture which are difficult to separate by conventional techniques such as the azeotropic mixture. Second is removal of volatile organic compound from the water. So if you have the wastewater which contains the phenol and other these type of compounds, you can use the perforation process to remove that compounds. Third is for maintaining the concentration of alcohol in the alcoholic beverage like beer or wine. So you can maintain the concentration of alcohol by removing the excess amount of alcohol from this beverage. Fourth is the removal of fragments from the flower juice. So if you want to produce the perfume in the perfume industry, you can use the perforation process to remove the organic compounds present in the flower juice which is responsible for the fragments. Fifth is the dehydration of biofuels. If you make the bioethanol or biodiesel as a fuel, then it contains the small amount of water. That small amount of water can be removed by using the perforation process. Sixth is the removal of sulfur containing compounds from the gasoline, especially the aromatic compounds. So like thiophene or benzothiophene, these are the aromatic compounds, aromatic sulfur containing compounds, and these compounds are very difficult to remove by the traditional sulfur removal processes. So we can use the perforation process to remove these compounds from the transportation fuel, especially the gasoline. One important aspect of this process is that this process is generally used to separate the minute amount of liquid solute present in the mixture. This process cannot be used to separate out the large amount of the a component which present in the large amount in the mixture. Why? Because here you have to, here the vaporization occurs at the permeate side. Suppose you want to separate a compound which present in the zero point 0.5 mole fraction or the weight fraction in the mixture. So what's happened, that amount has to be vaporized in the permeate side. So for vaporization you need the latent heat of vaporization, or you need the energy to vaporize the component, and that energy will comes from the liquid side. So what's happened, whenever you vaporize, whenever the vaporization occurs in the pervaporation process, the temperature of the feed mixture will drop. So if you vaporize the, so the a large amount of the mixture in the permeate side, or a large amount of feed in the permeate side, then the temperature of feed stream will drop significantly, and that will lead to the phase change in the solid state, or the, because diffusion is a temperature dependent phenomena, and absorption and desorption also a temperature dependent phenomena. So the amount of the diffusivity of feed species in that from the membrane will reduce significantly with the reducing temperature. So basically this process can only be used to separate out the compounds which present only the 1%, 2%, up to the 5, up to the 10% in the mixture. This process cannot be used to separate out any compound which present more than 10% in the mixture. Now the mass transfer within the membrane, yeah, based on in the pervaporation process. So here again we define a parameter which is similar to as the we define in the gas separation. Alpha is the separation parameter, separation factor or selectivity, that is equal to alpha a double dash divided by alpha b double w a double dash divided by w b double dash divided by w a dash divided by w b dash. So here w a double dash is the concentration of component A in permeate side. WB double dash is the concentration of component B in the permeate side. WA double dash is the concentration of A in the feed side, and WB dash is the concentration of B in the feed side. Suppose A is separating out selectively towards from the membrane. So suppose concentration of A is less than 1%, then concentration of B will be greater than 99%, and then if the membrane is not very much selective, then this term will leads to be WA double dash divided by WA dash. Okay, so they basically this represent the how much concentration enhances in the permeate side in comparison to the feed side. So if the value of selectivity should be higher than 1 or the lower than 1 for the separation of the separation in the pervaporation process. It should not be nearly equal to 1, otherwise separation does not occurs. So the transport of the molecules across the membrane can be divided in the 3 different steps in this process. First is the adsorption of permeating molecules on the feed side in liquid phase at the membrane surface. Second is the diffusion of these molecules through the membrane from feed side to permeate side. And third is the desorption of the permeating molecules in permeate side in the vapor phase. So in this process, vaporization occurs inside the membrane. Basically, when the molecules absorbed, this is the liquid side, this is the vapor side. So when the molecules of liquid absorb in the membrane surface, at that time the molecules were present in the liquid phase. Once they absorb in the membrane surface, so they have in the solid phase inside the solid structure, trapped in the solid structure. Then they will diffuse from the feed side to permeate side, and when they dissolve in the permeate side, then they dissolve in the when they reached in the permeate side and dissolved from the permeate side, they dissolved in the vapor phase. So the phase change occurs during the transportation from the across the membrane itself. Now no, as I told you that this process is used to separate the liquid mixture, and that membrane should have the higher affinity towards a single component which present a very minute amount. So the if the membrane doesn't have very high affinity towards that compound, then that compound cannot be separated out, because the composition of the concentration of that compound in the feed is very minute. You have to remove, you want to remove basically very minute amount of component present in the feed mixture, from the feed mixture. So basically, when the membrane has the so much high affinity towards a single component, and that component will absorb inside the membrane, then that polymeric membrane will be swell in presence of that component. So when the liquid molecule enters in the polymeric structure, the polymer start to swell, and when the polymer start to swell, then uh, the diffusion and absorption phenomena will change. The amount of diffusivity of that liquid molecule compound in the membrane will change. So basically this concept is called the anisotropic swelling, because this due to this swelling, the concentration, the term diffusivity term will becomes the function of the concentration. As the concentration of liquid, or as the concentration of the solute increases in the feed mixture, the diffusivity will increase exponentially, so it will affect the separation. So that's why in this pervaporation, diffusivities are generally the function of concentration itself. Now we will develop a mathematical model to calculate the fluxes in the pervaporation process. So as I told you that in pervaporation process, in the transport process, pervaporation transport process can be defined as the solution diffusion model, where the feed species first is selectively absorbed at the surface of the membrane, then diffuse across the membrane, then dissolved at the permeate site in the vapor phase. So suppose a partial pressure of a feed species in the feed channel is P dash, then this feed species will absorb at the membrane surface, then the concentration of that feed species become the phi dash, then it will diffuse across the membrane, then the concentration of that feed species at the other side of membrane will become the phi double dash, then it will dissolve from the membrane surface, then the concentration of that feed species in the permeate side will become the P, not concentration, the partial pressure of the feed is that species at the permeate side will become the P double dash. So the diffusion phenomena can be represented by the fixed law of diffusivity. So JV equal to minus d phi by dx, where phi represents the concentration, x is the direction, d is the diffusivity, and JV is the flux. So basically JV, the units of JV is mass per meter square second or moles per meter square second, based on the unit of phi. If phi is in the mole, then it will be the moles per meter square second. In phi is in mass, then it will be the mass per meter square second. And D is diffusivity. The units of diffusivity is meter square per second, and x is the distance or the thickness. It depends upon the thickness of membrane. Now we will start with the simple case. Suppose D is constant. Generally in this process, D is in the pervaporation, D is not constant. But suppose we assume that D is constant. Now phi can be correlated with the partial pressure of that feed species in the feed and permeate side by using the Henry's law, as we have used in the gas separation process. So phi equal to SP, where P is the partial pressure and S is the Henry's coefficient. So you can write JV equal to minus DS P dash minus P double dash, because here the constant in this process generally we assume S as a constant. So the Henry's coefficient will not change across the membrane in general. So here JV will become minus ds P dash minus P double dash divided by H, where H is the thickness of the membrane, P dash is the partial pressure at the feed side, P double dash is the partial pressure at the permeate side. Now the product of diffusivity and Henry's coefficient will become the P permeability. This capital P represent the permeability. So JV equal to minus P multiplied by P dash minus P double dash divided by H. Now suppose D is the function of diffusivity is the function of concentration. So generally in an isotropic swelling, the diffusivity becomes the exponentially depends upon the concentration. So D equal to D naught exponential of G phi, where G is a parameter, D naught is another parameter. So D naught is the diffusivity when phi equal to 0. Now we can substitute this term in the original Fick's law. So this is the original Fick's law, JV equal to minus D d phi by dx. So we substitute the value of D diffusivity as a function of phi in this equation. Now we can integrate that equation here. So after integration you will get JV equal to D naught D 0 divided by GH in bracket exponential of G phi dash minus exponential of G phi double S. Now where H is the thickness of membrane and now you can substitute the value of phi as a function of partial pressure by using the Henry's law in this equation. So here you can write JV equal to D0 divided by GH exponential of G S dash P dash minus exponential of G S double dash P double dash. Here we assume that the Henry's coefficient are different at the both side of membrane. At the feed side it is the H dash, at the permeate side it is S double dash. Now this equation can be used to calculate the flux across the membrane in the pervaporation process, where we assume the anisotropic swelling. That means the concentration of the diffusivity of feed species in the membrane will change with the concentration of that species present in the feed mixture.